A reaction that I wasn't going to tell you about because it's rather useless, but we might as well mention it now anyway, even if you find out later on how useless it is the hydration of alkenes to give alcohols. Now, if you just take an alkene and you react it with water, nothing happens. If you have it in the presence of an acid catalyst, H+, then you will make the alcohol, okay, the effective adding of HOH, otherwise known as water, across the double bond. Now, this is a regio-specific reaction. So if I take but1-ene, in which we've got that ethyl group effectively on the double bond, so it enables us to distinguish carbon 1 from carbon 2, and we react that up with water in the presence of an acid catalyst, we can either have the OH adds to carbon 1, or we can have the OH adds to carbon 2. If it adds to carbon 1, we make butane 1-ol. If it adds to carbon 2, we make butane 2-ol. Okay. Now, while you might observe a teeny little bit of the butane 1-ol, we're going to be very general and say that's not observed. Okay, because the hydroxide adds to the more substituted carbon. Here, there's carbon 2, you've got the ethyl on it. Hydroxide adds to the more substituted one. That is, of course, an example of Markovnikov's rule. So water adds across a double bond in the presence of the acid catalyst according to Markovnikov's rule. Now, the mechanism of this is relatively straightforward. There is our but1-ene from the side, and the H+ comes up. Now, the H+, of course, is an electrophile. Electrons move from the nucleophile to the electrophile, and so we get those pi electrons move to the H+. Now, that can happen in two ways. The H+ can go on to the more substituted carbon, carbon 2 that way, or it can move on to the less substituted carbon, carbon 1. Okay, if it moves on to carbon 2 here, well, then we've got a carbocation that is a primary carbocation, which is much less stable than what we see here, where the positive is on the secondary carbon. Okay, so two possible additions, one to the less substituted carbon, one to the more substituted carbon. If the hydrogen goes on to the less substituted carbon, then the more substituted has the carbocation, which is of course much nicer. Now again, if we bring in the water there, the water in this case is of course acting as a nucleophile. The carbocation is the electrophile, so the water can pop in there to give us this, which then loses a proton, giving us the butane 1-ol, which of course, as we said, is not observed because that would come from the primary carbocation. Secondary carbocation, there's the water pops in, the nucleophile, putting those electrons towards the electrophile. We make this here, which again loses a proton. I'm not going to worry about where that proton goes, but loses that proton to make the butane 2-ol, which is the predominant product. Now, the thing that's wrong with this reaction is it goes through the carbocation intermediate, and carbocations, as we saw to an extent when we looked at the Friedel-Crafts reaction, can rearrange. And because they can rearrange, you can have a mixture of products, which is, of course, yucky. But anyway, there we are, hydration, the addition of water across a double bond in the presence of the acid catalyst. You've got to have that acid catalyst to give you the carbocation. Because it goes via a carbocation mechanism, it's going to follow Markovnikov's rules. Wasn't that fun?